Today I wanted to bring up another pair of description of interaction and another description of motion, which are convenient to figure out the future also in certain class of situations. Yeah, because now, so far actually we discussed, well, practically two links between interaction and motion. Can we refresh? Could you refresh my memory? What were they? We had several laws which related motion with interaction. Yeah, because this is what we are doing all this throughout all the semester. We are trying to. We are describing environment, and what we want to do is, from looking at the configuration of the environment, we want to predict what the objects are going to do. This is the only thing which we are doing. Well, sometimes we can reverse the problem. Yeah? We want something to happen. So we want that the objects will start moving in a particular way, and then we design interactions. We put objects in the vicinity which will produce appropriate interactions to create this effect. All right. Yeah, so far we had two laws. Well, one is called law, one is called the theorem, which relate interaction with motion. What are they? Newton's second law and work energy theorem, both work energy theorems. Just to make sure that we see interaction there and motion. So which physical quantity in Newton's second law describes interaction? The force, correct, the force. And now notice that when we look at situation, at the configuration, we can recognize how this object interacts with the rest of the universe. And we have to consider the rest of the universe. However, despite we recognize that only few objects significantly affect that object. So there are only few objects which interact with a given object. All right, what describes interaction? Motion? Acceleration, correct. From acceleration, we can figure out what will be velocity, of the object, and what will be position of the object at any instant. All right, so this is what Newton's second law did. How about if we think now about work energy theorem? What quantity describes motion? Kinetic energy, correct. Kinetic energy, the faster object moves, the higher kinetic energy. It is directly related to speed, right? It is 1/2 of mass of the object times square of speed of that object. So if we know for a given object, if we know its speed, we know its kinetic energy. And what describes interaction? Work, correct. All right. Now the next pair is impulse and momentum. And the relationship between impulses and momentum is particularly useful in situations in which interactions are very intense but brief. The interactions are so intense that practically we can ignore all the remaining interactions. Can you find out a brief interaction which is so intense that the rest doesn't matter? A gunfire, for example, correct. Yeah, if you shoot a bullet, that bullet practically interacts only with the barrel of the gun. Gravitational interaction doesn't matter, air resistance doesn't matter, as long as the bullet is in the gun. Correct. What else? Find something else. In a combustion engine, we have this too. So the interaction between the gas and the piston is very brief. However, we have them, a lot of them. So really, when we are interested in the operation of the combustion engine, I don't think that we are going to use this theorem, although we could, because, well, we will be interested in the average effect over a period of time. So although it is true, it is applicable. I mean, in principle, actually, everything is applicable, because now, what does it mean, brief? Do we live briefly? Compared to what? Right. I mean, if you think about just even the age of Earth, each of us appears for a moment like that. I mean, this is how Earth would see us. I mean, I'm trying now to find something similar to how we see something. Yeah. So if this is how we see a click, and Earth sees our life that way. I mean, of an individual. Yeah. So our life is brief for the Earth. It is not brief for us. A click is brief for us. Well, these type of interactions, which we consider relatively brief and intense, are called collisions. And if galaxies collide, for example, it takes millions of our years, and it is still considered a brief interaction. In the life of galaxies, it's a brief interaction. All right, so I've described now when these type impulse and momentum are useful for description of nature. Now I want to formalize what is impulse and what is momentum. Let's start with momentum. Momentum is a quantity which describes how object moves. And by definition, if I consider just a particle, then momentum is equal to the product of mass of the particle and velocity of the particle. So if I think about an object, I could think, although we will introduce something which is called momentum of an object, and you will see that actually it won't be defined that it is mass of the object multiplied by velocity of the object. However, it is going to be equal to mass of the object multiplied by the velocity of the object. Why don't you repeat that last statement to your neighbor? What I just said, so concentrate. Yeah, because the definition of momentum is for a particle. Momentum of a particle is equal to mass of the particle multiplied by velocity of the particle. I just said in a moment ago that if we consider an object, yeah, because we can approximate object as a particle. And if we do this, then indeed this definition would be also good. So that momentum of the object is equal to mass of the object multiplied by velocity of the object, although it's hard to say which velocity. Later on we will see that it is velocity of the center of mass of the object. However, for an object, product of mass and velocity is not the definition of the momentum of the object. We will have another definition for momentum of an object. Now consult it with your neighbor. What did I say? All right. So momentum of a particle is always in the same direction as the particle is moving. Momentum is a quantity which describes, and momentum is quantity which describes motion, and since it describes motion, it is related to other quantities which describe motion. Well, we have already in the definition one of those quantities. Which one? Velocity, correct? So momentum is related to velocity. Velocity describes motion, momentum describes motion. So now, to whatever velocity is related, then momentum is related too. So, for example, we can see that if I, well, we will see in a moment, version of Newton's second law, which will relate momentum to force, because velocity is related to acceleration, so momentum is related to acceleration. Now, in a work energy theorem, what is the quantity which describes motion? Kinetic energy, which means that momentum must be also related to kinetic energy. How about if we find out that relationship? Why don't you help me actually to justify each step? So where did I get this step from? Why kinetic energy is equal to 1/2 of mass of the object and square of its speed? How do we know that? Yeah, Amber? You don't know? Somebody say something. Recover her. Save her. Yes? Where do we have this? Why kinetic energy? How do I know that kinetic energy is 1/2 of mass times square of speed? Mark, do you have an idea? From what integral? So when we calculated something, right? Integrated something, right? I'm not asking you how is it related to momentum. I'm just asking you how is it that kinetic energy is equal to 1/2 of mass times square of speed? Jessica, what's your opinion? Where is this from? From Newton's second law. And Mark, why are you Mark? Because the parents name you that. Right. Yeah, they assigned that label to you. All right. Don't you remember how we defined kinetic energy? What is the definition of kinetic energy? Tell me the definition of kinetic energy. Not a story about it. So don't tell me a potential that it is capability to perform work. Formal definition of kinetic energy. What is the formal definition of kinetic energy?
Mass times the speed squared divided by.
Correct. It is mass of the object square of the speed divided by 2. Right. Now, so why do we call it kinetic energy? Because it's convenient. Yeah, it is much convenient to say kinetic energy than 1/2 of the product of mass and square of speed. If you hate concept of kinetic energy, forget the name. Every time when I ask you about work energy theorem, say that the change in 1/2 of the product of square of mass, what I'm saying, that the change of the 1/2 of the product of mass and square of speed is equal to the net work. Physics will survive that thing. You can stop using name kinetic energy and substitute it by 1/2 of the product of mass and square of speed. I advise you, though, to remember kinetic energy, because some people will tell you kinetic energy. All right. Let's now go to the next step. Where did I get this thing from? Well, one thing is algebraic, because I have m squared over here divided by m, so I see that m's agree. 2 and 2 agrees. Now, I substituted square of speed with square of velocity, and what's the difference between the two squares? And what's the difference between the two squares? Oh yes, there is a volunteer, Cody.
It becomes a quantity squared.
Oh well, that one is quantity too. Speed is a quantity and velocity is a quantity, so they both are quantities. It's not exactly the same. Here we square scalar quantity. JD was right, yeah, because here we square speed. Now here we square velocity. What's the difference between them? That the result of one is a vector. Result of which one is going to be a vector? Square of velocity is a vector, right? No.
One's going to result in a vector, and they're multiplying two vectors in one.
Okay, well, we multiply these two vectors, velocity. When we multiply velocity by velocity, what are we going to get? A number, correct, because how are we going to multiply it? Using scalar product, correct. So we have two different products over here. Here we have square of scalar square. Here we have square of numbers. Now, if we have two vectors in the same a square of a vector, well, it will be, if I square using scalar product, I have to take magnitude of the first vector, which is magnitude of velocity is speed, times magnitude of the second vector, which magnitude of velocity is speed, so I have already speed square, times cosine of the angle between them. What is the angle between velocity and velocity? 0. Cosine of 0 is 1. So do you see that it gives, indeed, scalar square gives square of speed? Do you see that? Good. Why did I do that? Well, how about you justify the next step? I now wrote that this is square of momentum. How could I do that? By the definition of momentum, correct. This is by the definition of momentum. I can also recognize now that here I have square of a vector. What square? What square do we have here? How do we square momentum? Using which of the four products? Scalar product, correct. So here we have scalar product, which means that I have to take magnitude of the first vector. So it's the magnitude of momentum times magnitude of momentum times cosine of 0 degrees. Cosine of 0 degrees is 1, so I can also write down that way. What's the difference between this expression and this expression? Read the numerator. What do we have here? Well, square of what? Here we have square of momentum. What do we have here? Square of the magnitude of momentum. All right. So momentum described what? Interaction or motion? Motion, correct. Well, it is very easy now to show this second version of Newton's second law, which says that in an inertial reference frame, the rate of change in momentum of a particle is equal to the net force exerted on the particle. And actually, this is the, currently this is the most, the most universal version of Newton's second law. Only this version is true in all circumstances which we encounter. For high speeds, the previous version is wrong. It is that when we accelerate an object to speed close to speed of light, no matter how fast we push that object, its acceleration will be tiny. If something, Yeah, because we have speed limit. We cannot exceed speed of light. So no matter how fast we push, it is bound by that speed of light. Momentum, however, will be changing. I mean, those of you who will take modern physics, you will learn that mass of an object is not a constant value, and the faster we move, the higher is our mass. So it is more difficult to change our motion when we move fast. Taylor, you have a...
Isn't that only at like really high speeds, like close to the velocity of light?
Speed of light, yes, this is what I said, correct. If we move with the speed, if objects move with speed close to speed of light, force is not equal mass times acceleration. However, it is still equal to the derivative of momentum. And actually, if we take a look at that, we will see why does it happen. Because I want to show now that in a non-relativistic situation, indeed, the two versions of Newton's second law are equivalent. And then we will see actually why relativistic physics makes it different. All right, so if I start actually with this expression, that the net force is equal to the rate of change in momentum of a particle. Net force exerted on the particle. I can write down now that momentum is equal to product of mass and velocity of the particle. Well, if I now differentiate that, well, in classical physics, or as long as we move slowly, mass practically does not change with speed. So it's a constant. It's an attribute of an object, which is, or a particle, which is a constant, has a constant value. So I can pull out that mass in front of the derivative, and derivative of velocity gives me what? Acceleration. Why derivative of velocity is equal to acceleration? Because we said so, correct. It is our definition of velocity. So over here I will have now mass times acceleration. Which step would be not valid if we indeed assume that mass is not constant? This we could not take mass in front. How would we differentiate then this product using what theorem? Yes? You have an idea? Nope. We would have to use, yes? We would have to use product rule. Correct. So instead of single term, which we will have obviously first terms time derivative of the first factor multiplied by the derivative of the second factor plus derivative of the first factor. So we would have dm over dt multiplied by velocity. All right. So the quantity now which describes interaction, which is directly related to momentum, is called impulse. And impulse, in a way, in a similar way like work, describe cumulative interaction. Over in case of work, we were interested cumulative interaction over a path more than over a time interval. In case of impulse, it is over a time interval. So if we integrate force with respect to time, then we get a physical quantity which is called impulse. Here, now that work was, we had to integrate force with respect to position. So we had to add values of force at all positions along the path. Here we have to add it over all instances during the process. Well, so if I consider, I can think about time average value of the force. If we recall what is the definition of an average, it is integral of a function divided by the size of the interval. So I can recognize that this expression over here is an average value of the force. So if a certain interaction exists for a certain period of time, delta t, if I multiply the force times time interval, then I will get impulse, the same as this one. If a force of 1 Newton is exerted for 1 second, what would be the impulse delivered to that object? 1, correct. How about if there are 2 Newtons over 3 seconds? What will be the impulse? 2 times 3. If it is constant, then average is equal to instantaneous. So indeed, instead of integration, we can just multiply the two quantities and get it. All right. Finally, we get to the theorem which links description of interaction with description of motion. And it is referred to as impulse momentum theorem. And it says now how impulse changes depending on, how momentum changes depending on the delivered impulse. So we will now start with the change in momentum. I can write change in momentum that way. Why? Where this thing comes from. Which actually I notice on the test you often confused change of a quantity with the quantity. Like work energy theorem relates change in kinetic energy, and change in kinetic energy is not the same thing as kinetic energy. Why don't you talk to each other to illustrate that change in general is not the same thing as the quantity on an example of checking balance? Talk to each other for a moment to indicate that the change in balance is not the same thing as balance. So show your neighbor that it could be different. Also find the situation, indeed it happens that change in balance is equal to balance. Can you find a situation that balance is equal to change in balance? Amber? A judge? Yes, Taylor?
Wait, where change in balance is equal to balance?
Yeah. Under what circumstances change in balance is equal to balance?
Like if you have $0 in your checking account.
Aha, very good. If you had $0 yesterday, you made a deposit of $100, then change in balance is going to be $100. And what will be balance today? $100, right? So if initial value is 0, and this is quite often the case when we work with work energy theorem. But remember that conceptually it's a different quantity, and if Taylor had $10 yesterday, then and deposited $100, then change in balance would be $100, and the balance would be 110. Correct. All right. So delta P doesn't refer to momentum. It refers to change in momentum. And why is it that difference? Let me ask you then the question. How did you figure out that change in balance was $100? Final balance minus initial balance, whatever final and initial are, right? Because final meaning at one instant, initial meaning at earlier instant. Correct. How did you know that? Why did we subtract? Correct. This is how we define change of anything. Change is always comparing the quantity or taking difference of a quantity at two different instances. This is what is change. Except when a beggar asks for change. This is different change though. All right. Now I'm going to write this. Where did I get that from? It's a mathematical step. So those of you who are in Calc 2, that you should recognize. No, actually even 1. Where did I get this from? It's easier probably to see the other way. Who can see it? Yes, Andrew. So where did I get? Where is it from? What do you mean just? Yeah. Yes. Correct. It is just calculating difference of a function. What function? We say?
Function of momentum related to time.
No, it's not function of momentum. I mean, if we take a look at the tables of indefinite integrals, if I wanted to use fundamental theorem of calculus, which formula I would use? Yes, Amber? Yeah, yeah. I mean, obviously they don't have p; they have x's. So what integral? If I use x as the variable, which function were I integrating here? If the variable is x. It's integral of dx, correct. It's integral of dx from, let's say, a to b, from one value limit to the other one. Okay, so now, so what is the integrated function, by the way? Note x, Mark is right. What is it? 1, which means x to 0, right? So indefinite integral is going to be x, correct? Now I have to plug in values a and b, right? So it will be b minus a. Now, here I have to integrate. So a is p1, b is p2, p is x. So if I integrate that, I should get the top and plug in top and bottom values. Right, so this is b, this is a. Now p1 and p2, I refer that these are at two different instances. This is at instant 1 and this is at instant 2. So I wrote it in terms of corresponding time. This is really p2, this is p1. Do you see that? All right, great. Where did I get that from? Well, instead of dp, I wrote that it's f net times dt. Where did I get this from? Not from the definition. It's from the previous slide. On the previous slide, I had that the rate of change in momentum of a particle is equal to the net force exerted on the particle. So if I multiply both sides by dt, I will have that the differential change in momentum is equal to the net force exerted on the particle multiplied by the time when it was applied. So this is how I wrote that. And since I'm changing now the variable from momentum to time, I have to change the limits as well to the corresponding limits. So I have to put time when when we had this value of momentum, and over here time when we had that value of momentum. Now what's that? How about if I write? Oh, I wrote it. Oh, no, I didn't write it. Actually, what is now the name of this integral? Impulse, correct. So this is impulse. This is impulse of the net force. So change in momentum of a particle is equal to the net impulse of the, or you can also say the impulse of the net force. All right. It is, well, a third relationship between motion and interaction. On the right-hand side, we have description of motion, change in momentum. On the left-hand side, we have impulse, which describes interaction. Okay, now how about I have a puzzle for you. I will try now to confuse you, because you are not sufficiently confused, and confusion actually leads to the learning process. It's very efficient. So the length of the rifle is 1 meter of the barrel. So the barrel is 1 meter long, and well, when we shoot the projectile, it is going to leave the barrel at 500 meters per second, and it will travel through the barrel in 5 milliseconds. What is the average force on the projectile? I'm not saying that actually this, I'm making obviously this problem more complicated than a constant force, because if it were constant force, if we had a constant force, then the average would be the value of the force, so it will be quite easy to find, right? I mean, let's find out what would be the constant force if the acceleration was constant, right? Because if the force was constant, acceleration would be constant. So if it assumes speed of 500 meters per second in 5 milliseconds, so what was the acceleration of that bullet if it were at constant? Well, so I have to divide 500 meters by 5 milliseconds. So this is 5 times 10 to the power of 2. Here we have 5 times 10 to the power of minus 3. So 5 and 5 cancels, and we will have 10,000. All right. 10,000. Now I have to multiply it by 10 grams, and I can find, and that way I can find what was the force, the net force, if it were constant. However, in the barrel, the force is not constant. It varies. It is stronger, I mean, 0 at the beginning, then when all the gunpowder burns, it's the highest, but at that time bullet moves somewhere, and then as it expands, as the gas expands, it gets weaker. So the force is not constant. All right. Now oops. I'm going to solve it 2 different ways. I can calculate change in kinetic energy, right? Initial kinetic energy here was 0. Final kinetic energy was mass of the bullet times square of the speed over here divided by 2. And this is supposed to be equal to what? Change in kinetic energy is supposed to be equal to what? Work, correct. Net work in principle. But over here I can assume that all other forces except the force exerted by burning gunpowder are insignificant. So I will just write down that this is work done by the gunpowder. And I will write down that there was a certain average value of the force multiplied by the length of the barrel from the work energy theorem. if I solve now for the force from here using the given quantities, I will get that the average force was 1.25 kilonewtons. This is if I use work energy theorem. If I used another solution using impulse momentum theorem, well, momentum of the bullet over here was 0. Over there was mass of the bullet multiplied by velocity of the bullet. Well, in order to take magnitude, and actually I can find that, well, I mean, this is the magnitude of the change in momentum. So it is supposed to be equal to the magnitude of the delivered impulse. And magnitude of the delivered impulse will be average value of the force times the length of the time interval in which it took place. So if I plug in values now over here, since this is 0, so really I have magnitude of m times v, mass times velocity. Mass is a number, positive number. I can take it in front of magnitude, and magnitude of velocity gives me speed, right? So over here I can plug in 10 grams multiplied by 500 meters per second is supposed to be equal to that average value of the force multiplied by 10 milliseconds. And if I calculate average force, I will get that it was 1,000 newtons. I will leave you as a puzzle. This question is the puzzle which I want you to think over and give me the answer tomorrow. So this will be all for today. Thank you.